Hello, this is Sequential from Postec, and thank you for inviting me to this. And I'm really pleased to share one of the recent work in my group to you guys. And as you can see on the title, it's physics for AI versus AI for physics. Actually, there are two different topics. And for physics AI, what I mean by that is that I think in the previous presentations, a lot of speakers mentioned the physics-informed neural net, shown in pins. And I'm going to show you some of the advantages of that. And the second topic is AI for physics. So it's data-driven scientific discoveries. So these two are going to be the main topics for today's talk. And before jumping to today's talk, I want to take some moments to think about the mechanical engineering's AIs. As you all know, that it's design and manufacturing problems and mechanics, materials, and simulations, dynamic controls. On the other side, AI is data analytics, and you already know it's machine learnings and deep learnings, and even for the reinforcement learnings. So we all believe that AI is for mechanical engineering. AI is going to be the new tool to better understand physical or mechanical behaviors, or to discover better design schemes. So what I'm interested in here is that I want to bring and develop state-of-the-art of AI technology for mechanical engineering problems. So there will be the main motivations. And let's think about direction of deep learnings in the physics or mechanical engineering disciplines. So actually here I represent three different categories. So the first thing is that data-driven AIs. I mean, you already know that instead of having physics to understand it, we can collect some data from the mechanical or any kind of engineering systems to get some AIs or machine learnings and deep learnings to figure it out, to discover the general or hidden behaviors. That's what I mean here is pure data-driven AIs. The one in the middle is that I would say knowledge-guided AI or physics-informed AI. And we all know that there's if we know some knowledge or physics into the systems or applications that we have, I personally believe that there's no reason that we're not going to use that. So in the physics-informed AIs, the question is how we embed or combine these two physics and the data together. And the last topic or categories that I defined here is data-driven scientific discoveries or knowledge discoveries. In some case, suppose that we have no idea of physics or what's going on in the system that we are interested in, or the system is too complicated, so there's no way that we can understand. In that case, we are hoping that from the data, is it possible to find out or figure out some scientific reasonings or discoveries? There will be the last topics for. So in my presentations, I'm going to from the first to the second and third. So the first is the data-driven AIs. I believe that most of them are familiar with. So in order to give some explanations, I'm gonna use the wave propagations is scattering physics as a examples or demos. So if you are not familiar with the wave propagation, that's okay, because I'm just gonna use as one of the examples or applications. So if you think about sound or wave or pressure, whatever, it's wave scattering parameter from scattering object. So you can think of the wave is transmissions, reflect, or observe scatterings. So this will be the applications that I'm interested in. So in many cases, we already know all the physics. We know how the wave propagated, how to scatter or reflect when the wave pressures hit the object. So in many cases, if that's simple enough, probably we can solve that some kind of governing equations. In most cases, it would be the derivatives. And if some have these the complicated object, probably we have to use the numeric simulations model. So we can simulate it so a positive pressure field, like we can see on the right side. And here, this is the definition that I have here. So I want to use data-driven method. I'm going to assume that the AI have no idea on the physics. So how do you use the data set to figure it out or to predict the way the field whenever we have some kind of arbitrary object in the middle. So let's think about the simple approach that we have. So we can, I guess the first thing is maybe to supervise learning. So in order to have supervised learning, to teach AI the wave propagations, we need input and output at the same time. So we need input for the training data set, and probably we need at the same time we need output for the training data set as well. So for input data is that the object that I'm going to put it in the middle, right? But object is it's a randomized, so we don't know. So in order to teach the AI models so this here is we parameterize geometry of the objects that we're going to put it in the middle. But of course, we are not able to cover entire the object space. Probably it's going to be some of them. So, and the corresponding outputs, I mean, we have to run the numerical simulation models. So this one is with as you can see, this kind of animation is going to be outputs. So if you think about supervised learning problems, single image as inputs, and arbitrary object put in the middle, and the output side we're going to have like sequence simulations results going to be the output of this supervised learning framework. So how do you think you can teach this the training data set for the data-driven method? The thing is that the difference is we have sequential data set, I mean the outputs, and we all know that these are dynamic behaviors governing by some kind of physics that we suppose that we don't know. And let's think about neural net models. Since this is the image, and we can use some kind of convolutional neural net. So in here we use the convolutional auto-encoder type of networks that we can generate. And instead of putting this input and output, since we know the sequential dynamics behaviors, probably and we know that all of dynamic behaviors is related to the time intervals, like d over dt's. So in order to have this neural net is able to pick up the dynamics, probably we can put 2 or 3 consecutive input images, and in the corresponding outputs will be like another image at time t+1. If we have a bunch of the data that we generated from the numerical models, we can teach them, and hoping that this kind of the convolutional autoencoder type of models is able to learn from the training data set. So this is the outputs that we have, and ground truth and predict. What do you think? You think and another object again is ground truth and predict. If you more favor of AI, probably you might say it's the AI model. It's at some level is able to catch the physics, and if you on the physics side, probably this error is too large, and you're not gonna agree that the model is. I mean, the approximation error is huge. So in order to see that, the first law is ground truth, and the second is the predicted out of the models. And if you subtract, these are the errors for discrepancy between the simulation models and the model that the AI models. So the good thing is that since we know the physics, I mean, we know that it's dynamic behavior. So it's good thing about this, the data-driven, is that we use the sequential dynamic has been considered. But don't forget that this is still data-driven approach, right? So, and now this is the time that we have to think about why deep learning needs physics, and we all know that it's data-driven, is a black box. The outcomes are basically physically inconsistent. Right? Think about if the data is coming from the physical system, so data itself is physically consistent. Right? But the AI model doesn't have to learn the consistency. So there's no guarantee on that. And in many cases, the training or testing input and output relations looks good in many cases, but I don't think the AI model is knowing the fundamental things like sparse and low dimension things like in the previous presentations. So in other words, it's within the sample predictions and out of the sample predictions, it's poorer on the generalizations. So the last one is that interpretabilities. Again, like the previous Professor Clinton's talk, it's interpretabilities and the generalization. These are the big issues on pure if you decide to use the data-driven method only. So now it's time to think about the physics-informed neural net. And as you can see, if we do have a prior knowledge on scientific theory or whatever, there's no, I mean, we have to take a full advantage of that to increase the predictive performance. And when you think about the AI or deep learning models, always people are complaining data imbalance problems and data shortage problems. I believe that the physics inform is one of the most promising way if we integrate these to overcome these kind of imbalance or data shortage issues. Now let's move on to knowledge guide or physics informed AI examples. And these are the taxonomy of physics informed neural net. And in the first columns, there are many different deep learning models like ANN, CNN, RNN, whatever. It really depends on the data type that you are thinking of. And now the middle column is that we have many different knowledge representation methods. I mean, one of them could be like differential equations or some kind of algebraic equations, or even for the graph, right? If you know some the entities and the correlations and causal relations, probably we can represent that the knowledge into graph representation forms. And even like CAE simulations outcomes, it could be another type of knowledge representations, and human experience and domain knowledge. And the last column is how you integrate those knowledge into neural net in many different ways, but here I only represent 3 of them. The first thing is the feature engineering. Feature extraction is, I think, one of the most powerful and most easiest one where you can embed the physics knowledge into the model. And the second thing is design. What I mean by design is that if you know, here is designing the structure of the neural net. Suppose we have many different inputs, and if you somehow, if you say, suppose you know that these 2 groups of inputs has nothing to do with each other, probably we can separate things and combine it at the end, downstream of the neural net. And the regularization is the most interesting that I'm going to continue explaining in the following slide. So this is typical architecture of physics informed neural net. Think about the problems, and suppose you have some data set, probably it's going to be small data set, as well as the physics represented by ODE or PD, whatever. And the idea behind is that neural net is universal function approximator. Just we can approximate any kind of functions or outputs. Here, in this case, it could be function of U. And since we have some data set, probably this is the typical way of defining the loss functions. Like given data set and the output that the neural net is predicted, we have to minimize the loss. And suppose we have any kind of physics informations like, for example, this kind of partial derivative equation. And we put it in another loss functions. So we call it as regularized. It's going to, we can think of consider it as a regularization. So remember that it's regularized by physics and matched with the sparse data set or small set of data set. That's the typical way of architecture, typical architecture of the physics form. So by doing this, we can force the neural net to follow the sparse data set as well as the physics. So now let's go back to the original problems that I defined here and raise the wave physics problems. Now we know that all the wave physics is like that. And if you think about the problems, is we want to put arbitrary object in the middles to then we have those we're gonna work as boundary conditions. So here, again, in the same framework, and we just take the derivatives twice over time and from x and y in the space, and these are the boundary conditions. And this is kind of another one. Think about the boundary conditions on the object, because we know that the object is given, so we already know the shape, and we can define the boundary conditions that the neural net should follow. So having that, I'm going to skip a lot of things between, and I'm going to share the result over here. In the first column is ground truth, and the middle column is proposed, and in order to make some comparison, the last one is baseline. It's the only data-driven method, and the total wave and sketch total wave is coming. So it's right before the wave is touched object, so all pretty much the same. Now, once we have that, it's scattered. And as you can see, ground truth and proposed are very, very identical, similar, but in the baseline. Now, let's move on to. So here, I mean, I can give some quantitative ways, but here is and you can look at the figures, and these are like 3 different scattering waves, but the baseline for the only data driven is totally different. So these, and another comparison that we can do is that direction. The reason why we are interested in the sketching patterns that we want to say this is ground truth and the wave field, and these are the proposed and another baselines here. And we want to know the direction of that. Sometimes we want to actually control the wave field having different object in the middle. So you can see these are pretty much, but here the one is using the data driven is not that accurate. So finally, it's a physics informed neural net. There's a lot of advantage over that. One of the things that I mentioned, that generalization performance. In order to show the generalization performance, what I did is that, say here, this is the low dimensioner. I use the dimension reductions. These are the data set that we use for the training. And here we intentionally, because I want to show you some expert generalization performance. So these are the data set is not the AI models haven't seen in the training phase. But as you can see in proposed models, since they learn the physics, you can generalize things. It doesn't have to restrict the within sample performance. So that's one way that we can demonstrate the advantage of physics in some of the models. The final topic is that data-driven knowledge discovery or scientific discoveries. And this could be one of the motivations they hear. If you numerous natural phenomena described by concise mathematical expressions, not the AI models, not the black box. So if you think about, say, in histories like planet positions, there are a lot of observations and measurement. Out of those observed measurements, calculus invented calculus laws, and Newton's and created universal gravitation laws. So here, what we did is that from data set, actually humans did a kind of like generalizations and trying to find out close to mathematical expressions. What I want to do is that instead of human beings doing that, I want to ask the AI to figure out the closed mathematical expressions. So it's a field of symbolic regressions, and it's trying to discover the closed form expressions to provide simple yet accurate fit to given data set. Again, it's going to give us interpretabilities and generalizations. That's one of those two weaknesses of the deep learning models have. So if you think about, probably again, it's X and Y is input and output. We're trying to figure out the relations. And what AI model does that we don't know what's going to happen inside. But if you have good models, if you give me the inputs, I can predict outputs. So nobody knows how it works inside. So instead of having deep learning models, probably we need some kind of equations. Suppose it can be sine and cosines, log, or whatever. It can be the polynomials. So I don't think I need to more emphasize the advantage of having the closed mathematical expressions over deep learning models. So key idea is that any kind of mathematical models can be equivalent to transform tree structures like this. Okay, so in the tree structures, that means if you are able to build some kind of tree structures, we can convert it to the mathematical expressions as well. So let's think about, this is a combinatorial problem. So now we have to think of all the possible cases. We have to combine them to see. And you know that this is NP-hard problems, and the reason why is that if you have more like operators and inputs, it's going to be growing exponentially, the searching space. So it's almost impossible. So what we did is a human thinking strategy. That's I think what we did, or like GA, like evolutionary computation method that we've been trying to do. And now I want to think mathematics as language models. What do you mean by that is that we have mathematical expressions, and we can convert it to tree structures, and the tree structures we can convert the sequence. What do you mean by sequence is that, let's say we have this divider sign and multiplications constant x and the log and 1. We can define the sequence if we have tree structures. The sequence models is that now we can consider as sequence as language models. Then we can utilize the natural language processing. So again, starting from the equations, and now we have this kind of the mathematical language model that can utilize to optimize. Okay. Now this is like the starting of the sentence, end of sentence, and now we have vocabularies in between. In order to make sense on some kind of sentence, we have certain patterns, or we have some kind of finite combinations out of it. So this is now is optimization problems. We have to optimize the sequence of the sentence of the links over here. And how do you optimize it? And that's kind of, so we decide to use a reinforcement learning. So I'm not going to go in too much details, but we define reward and state actions to manipulate it during the optimization process. So as a summary, so view symbolic regression as language, natural language processing is mathematics as a language, and language models then we utilize reinforcement to optimize to find out the optimal sequence of, then we can find out the mathematical expressions. And in this field, Nguyen symbolic regression benchmark, they have defined like these 12 expressions. And as you can see, these approaches are from the data set. We add a lot of noise and some uncertainties, so we are able to find out these equations. Instead of having deep learning models, if we have these equations, we can increase the interpretabilities and the generalization performance. So discrete sequence optimizations, and for today's topic is that what I did, I mentioned closed form expressions. This is from the data set. I want to find out some kind of closed form mathematical expression. That's what I mentioned it. And another thing is that differential equations, like in the Professor Thornton's presentations talk, and many dynamic behaviors can be represented by differential equations. So from that data set, I want to find out differential equations. So it's different from finding differential equations from find the closed mathematical expressions. And the last topic is that suppose we have differential equations like that. I want to solve that. Right? That's another the researcher from the Boston University. They try to use a physics-informed neural net to find out closed solutions out of the differential equations. Summary. Like here, eventually what we want to do is we try to have better understanding of physics or mechanical or any kind of engineering problems. In order to that, given the engineering systems, we can utilize governing equations or first principles, whatever. And another approach is that having a lot of data, we can figure it out. These, say, any machine learnings or deep learnings, AIs. Now, what I want to say is I mentioned many things from this side, but I believe actually we have two approaches or two weapons to get here. So AI is just one of the approaches or methods. And the last one is that if we have big data set, a good quality of big data set for each class, probably data-driven approaches might work. But personally, I don't think there are many such cases in real case. And most of them we're gonna face to the small data set problems. In that case, I believe that physics-informed neural net is one of the approaches that we can try. Yeah. So that's all presentation that I prepared for.
Okay, thank you very much.